Hello, everyone. So today we're working on Chapter 6, which is about momentum. We'll be looking at momentum and impulse and how impulse changes momentum. Now, most of us already know what momentum means, and we use that word correctly. In that, we talked about something that seems to have some sort of motion to it, some inertia that's going to keep it going. So we'll say, yeah, that's got momentum. This momentum, of course, is the physics type of momentum. And when Newton said momentum, he was talking about inertia in motion, is what he called it. Inertia, remember, Galileo talked about inertia as that resistance to change in motion. And Newton also defined it as the mass, or related it to the mass. So, what we're talking about is a mass in motion. Now, the boulder here, you can see it's rolling down a hill, and the man is moving too. So, we've got lots of inertia in motion. Now, the formula for momentum is very simple. The formula is just mass times velocity. So something with a mass, something in velocity. And this is a simple equation for it. Strangely, light also is considered to be able to apply an impulse and to have a momentum. So it's not as simple as this formula all the time. But certainly anything that's a mass that is moving, that has a velocity, then it has a momentum. Now, we don't have any new unit for momentum. You just use the units that are available. But one thing that's a bit confusing is the symbol for momentum. That symbol is called rho, the Greek letter rho. And so rho is the symbol we use for momentum because we've already used m for mass. And so we can't use m for momentum also. And so we use this rho symbol because it looks sort of like a P, and it probably relates to impulse is where that comes from. Okay, now there's no special unit, so let's just go do an example. So here's a car that is 600 kilograms in mass. It's 40 meters per second in speed. So all you do is multiply those together. And so 6 times 4 is 24. Add on my zeros. And I've got 24,000 kilograms meters per second. So I'm just using the units that I already have, and I don't need any new units. Now, one thing is this really was just 40 meters per second. We didn't say north, south, east, west. So really it's a speed, and that's okay. Especially for this class, direction is unimportant. We just say momentum is mass times speed. But we're still going to spell it mv for the formula because v is much more distinctive again than an s. Now, momentum comes in all sorts of surprising ways. So you could have something that has high mass and high velocity, like the planet Earth. It's moving fast, and it has quite a large mass. Sometimes, though, you can have things that have high mass, but they have a low velocity. So you might have a very big cruise ship or a train that has a very pretty large mass, not as big as the Earth, obviously, but they are moving very, very slowly as they're coming to a stop. So their momentum would be reduced, and they would have very little, really. Now, one of the most interesting is when you've got a low mass but a high velocity. Well, that would be like charged particles like electrons, certainly very light and in mass, and they can be moving close to the speed of light. And then you've got things that have a low mass and a low velocity. Now, a raindrop has more mass than an electron, but still, compared to a train, it's a small mass. And so you've got all these combinations of things. So sometimes you could have something that has a high mass and a low velocity, but it's got the same momentum as something that has a low mass and a high velocity, right? So you could have something that is a high mass, so let's just give something, let's say it has 5,000 kilograms, but it's only moving 1 meter per second. Or you could have something that is very small, 1 kilogram, moving at 5,000 meters per second. And those would have the same momentum. Now, as we're going to find out later, it may be the same momentum, but it would be different amounts of energy, actually. So that is something we'll talk about later. All right, and so here is an object that has a large mass, but it moves very slowly. So this is the Space Shuttle Mobile Launch Platform and Crawler Transporter. So these big platforms were used to carry the space shuttles out of the garage, and then they actually launched right on them. And they move very slowly. So they only go about 1 mile per hour, but they are 17 million pounds. Okay, so their momentum is still a large amount, even though they're only going 1 mile per hour because of that huge mass and doing it in the metric system. It comes out that their mass in kilograms times their velocity in meters per second still comes out to be millions and millions of kilogram meters per second. Okay, so just put the units together, and that is what you can use for momentum. Usually we use kilograms and meters per second, but we may use centimeters per second at some point. We may use a mass in gram at some point in the lab. Now, because this formula is so simple, of course, when you double the speed of an object, what happens to momentum? It's just doubled also. Okay, so let's talk about impulse. Impulse is where you're applying a force for a time. So we use the word impulsive. So we're saying, oh, it was an impulse thing, you know, you bought something on impulse. So not quite the same thing. Unless you're saying that, you know, you bought that candy bar in the lane because it forced you to over a certain amount of time because you were standing around waiting at the checkout lane, right? So anyway, so that could be some idea of the same idea. This is applying a force for a time, and anytime you apply a force, there is a time connected to it. You can't apply a force for 0 time, or it's not applying the force, right? There's no interaction. So you apply a force. Maybe you're pushing on this car with 100 newtons of force, and you push it for 10 seconds. And so you can see that simply you'd have 100 times 10, force times time, and that would come out in Newton seconds, right? 1,000 Newton seconds, very easy. Except what does it mean? Well, this is how you can change the motion of something. You apply a force to it, and like this car would get started, you apply a force and you change the motion if you have a net force. So a great force for a long time makes a large impulse, so you're usually able to change the motion more if you have a greater force for a longer time. So if this guy could keep applying a larger force or for a longer time, he could get that car going faster. If it's a shorter time, that's a smaller impulse. So in baseball, we often change the motion of a ball with a bat. And so the idea is that the impulse, the force times the time, changes momentum, mass times velocity. And so the formula for that comes out to be force times time equals change in momentum And we're using the delta symbol here. Remember, the delta symbol would mean final minus initial. So the delta mv would be the mass times the velocity final. So it changes its speed minus the mass times the velocity initial. Now, sometimes it's the mass that changes too. That can actually happen also. So the whole momentum, maybe you're changing the mass, maybe you're changing the velocity, maybe it's both. Okay, but the finals minus the initial. And so in this case, though, remember this should be the net force. That gets left off the formula a lot. And so yes, we're really talking about if a net force is applied, then that will change the momentum. Okay, so net force is what changes momentum. Because if you've got no net force, then it's not going to change it, right? So there's no push either direction. Pushes are balanced, no change in momentum. Now, in baseball, this is where your coach says follow through. Again, the baseball bat remains in contact with the ball, and it applies that force for a certain amount of time. And so because of that, you're going to get a change in the momentum of that ball. Now, if you apply a big force and keep your bat in contact with the ball for a long time, then maybe you've got a home run. Okay, if you only apply a small amount of force, just enough to really bring the ball to a stop, then that would be maybe like a bunt. You're just bringing the ball to a stop, basically. And so so those are useful too. So anyway, so yes, so that's the difference of the force that you apply and the time that you're in contact. And the same thing for a pitcher. A pitcher, when he's throwing a baseball, okay, he tries to remain in contact with that ball for a long time. So the ball goes way out, you know, he's got his leg up, he's got his arm way stretched out, and then he brings it back the other direction as far as he can before he lets go. And what he's doing is applying a force for a long time so that he can give a great change to the velocity of the ball. Okay, so here's a baseball player applying a force of 60 newtons to a baseball for contact time of 3 seconds. What is the change in the momentum of the ball? Okay, so force times time, and that should be the net force, right, equals the change in the momentum. So if all they're doing is asking for the change in the momentum, then I just need the force times the time. So my change in the momentum is going to equal the force times the time. And so that's going to be my 60 newtons times 0.3 seconds. Okay, so 60 times 0.3 is going to be 18. And that's going to come out to Newton seconds, as we talked about. Now, is that really going to equal m times v? Well, let's check on that. M times v would be kilograms meters per second, right? That doesn't look like Newton seconds. Okay, but a Newton is created out of other units. A Newton is a mass times its acceleration. So a Newton is really a kilogram meter per second squared, because that would be mass times acceleration. That would take care of newtons, right, by Newton's second law. And then we're multiplying by a second. Well, that cancels out one of the seconds. And sure enough, we would end up with kilograms meters per second, just like on the other side. So yeah, the units work out okay. All right, in physics, we've got this all figured out. The units should work out as long as you're using the right ones. Okay, so that was the first question. All right, the second one, if the ball has a mass of 0.2 kilograms, what was the change in the velocity? Okay, so in this case, one of the things is that the mass isn't changing of the ball. So we don't have to worry about the mass. The ball's not ripping apart or anything. And so when we're writing change in momentum, which would be mv final minus mv initial, we don't have to worry that the mass is actually changing. We just need to think about the velocity that's changing, right? So that's what we want to know here. What is the change in the velocity of the ball? Okay, so we can pull the mass out to v final minus v initial. Okay, so that's what we want to find. And that's going to equal the impulse, the 18, right, that we already figured out. That was the impulse. That was the change in the momentum. Okay, so those two things are the same, right? Impulse equals change in momentum. Okay, so we've got the impulse, which is the change in the momentum. And now we know that that's 18 Newton seconds or kilogram meters per second, same thing. And that's going to equal our mass, which is 0.2 kilograms, times our change in the velocity, delta v, v final minus v initial. Okay, so all we have to do is, kilograms, is divide by that 0.2 kilograms on both sides, and that will give us our change in the velocity. So our change in the velocity, delta v, is going to equal 18 divided by 0.2. And so that's going to become 90 meters per second. Whoa, that's really fast. Okay, so I just wrote this problem the other day. I was thinking 90 miles per hour, 90 meters per second. That's a really big change. Okay, but it could happen. If the ball was coming into the plate at 100 miles per hour and the batter sends it back at 100 miles per hour, well, that would be about a change of 90 meters per second altogether. Okay, so yeah, so it is possible, but boy, you got to have some heavy hitters and some fast pitchers there. Okay, all right. Okay, so these equations you can use to find out the changes in velocity and by knowing how much force was applied and for how long. Okay, now impulse does change momentums. And so here are just some examples of increasing a momentum. And of course, you apply that force for a long time. And so we were talking about follow through. For coaches is that long time thing. You stay in contact with the ball, whether it's golf or whether it's baseball or even volleyball. You want to be able to move with the ball, and basketball too. So that's going to be a great change in momentum. So golfers and also things like cannons, if the longer the barrel, then the more time that the gases get to spend in contact with the cannonball, right? So they're pushing the cannonball, applying a force, and so that ball will go faster and faster in the barrel. And this is why rifles have faster speeds for their bullets than a short gun. Okay, so why does that work? Why does the cannon with the long barrel produce a cannonball that has a greater speed? Well, is it receiving a greater force, a greater impulse, both? or neither? And let's just think about that. Is it a greater force? Well, we don't know if there's more um, powder put in to make this cannon go. That's not necessarily the idea. What's the idea here is impulse, right? What is impulse? It's the force times the time. And that's what's getting greater there. The long cannon applies force for a longer time. Oops. Okay, so one of the cool things about this is that this is very useful. It's the time that matters, and that will actually change the amount of forces. So we want to bring something to a stop, like a car or a truck here. The truck has a certain amount of momentum. They're going too fast and they're going off the road. So the thing is, if they hit something like a haystack and they slowly destroy the haystack, so not many haystacks nowadays, but think about bushes. You know, if you hit some bushes, then you're destroying the bushes as you're driving through them, and they will bring your car gradually to a stop. And so in that case, you've extended the time of the collision, and that makes for a smaller force. But if you take that same truck or car and you smash it into a brick wall, well, then what happens is that there's not much time. There might be a tenth of a second. A short time means a large force. Okay, so it's the same amount of momentum in each case, same impulse. So you're changing the momentum, which means that you have a certain amount of impulse. But that force could be a small force that you apply for a large time. So force down, time up. Or maybe it's a big force that you apply for a small time. So the force increases as the time decreases. Okay, so there's a trade-off here. And this is why in movies, when I see someone who their brakes go out because, you know, the bad guys did it, and their car is careening down the road and they're very carefully trying to stay on the road. And they shouldn't be. They should be hitting bushes and mailboxes and other things to try to bring themselves to a stop. Because all they're doing is making themselves go faster and faster by avoiding being hit. Okay, so next time you're in a car without brakes, and it can happen, and you're in some place like San Francisco with steep hills, then start hitting things, okay, you know, so you can come to a stop. Okay, and so in life, this happens too. That's why you're told to bend your knees when you jump down so that you you're going with your weight. So that makes a longer time, smaller force. In boxing, you ride with the punch, so you lean backwards, and then the punch is not going to hurt you quite as much, okay? Same thing, this is why car airbags work. The car airbag, your face is going forward. You don't want to hit the dashboard. The dashboard is harder. It does have a small layer of material on it. But yeah, you're going to come to a stop one way or another. But it's better to come to a stop using a big fluffy pillow, the car airbag, than to smash your head into the dashboard, right? I've got scars on my head from smashing into something in the days before cars all had seatbelts. They didn't have seatbelts in the back. So your little kids had no seatbelts. So I've got scars from smashing into the seat ahead of me because there was no seatbelt in the car. Anyway, so yeah, so with an airbag, people are surviving greater wrecks because what happens is the force goes down because the time goes up. It's extended. And so it's like a bungee jumping. Okay? When you're bungee jumping, you're going to come to a stop one way or another, way down below the bridge that you just jumped off. And so bungee cord or no bungee cord, doesn't matter. If you're going to come to a stop, well, yeah, it matters. When you're jumping with a bungee cord, then what happens is that the bungee cord, once it starts to extend, it's tied to your foot, okay? So once it starts to extend outward, go straight, it starts to apply a gentle force backwards, right? And so what happens is that you are gradually brought to a stop by this gentle force. Whereas if you just hit the ground, then you're just all crumpled up. And usually a collision takes about 1/10 of a second, that whole hitting the ground thing. So anyway, so bungee cord or no bungee cord, hopefully you would pick the bungee cord, right? Longer time as the cord stretches out. You still might get to the bottom of the valley, but a gentle force on your feet as opposed to hitting face planting into the sidewalk. And so when you see people doing acrobatics, I like to see a safety net. But the same idea, when they hit the net, it stretches, right? So they can happily stretch with it, longer time, smaller force, and they survive. Okay, so that's the end of that part, and we are going to go do more stuff. Okay, so I'm going to stop this recording and pick up part 2.